talked about ANOVA. We talked about a post hoc test for ANOVA. We talked about correlation and regression. And this is the last one. This is chi-squared. Chi-squares are a little bit different. Well, all of these tests are different from each other, which is kind of an important thing. So you, again, in each of these tests we're talking about, you just don't grab one off the shelf because you think the name is cool. There's a reason for it, and you always have to know the reason, because someone in the future, I don't know, maybe sometime next week, is going to ask you, what is the purpose of such and such a test? And you need to be able to tell that person that you know what that test is for. Okay? When is that? When do we have an exam coming?
Tuesday.
Tuesday? Okay. That's too bad, because I usually, if tests on Tuesday, I always make them tougher than any other day. That's all right. You'll be okay. Okay. All right. So chi-squared analysis. What's it for? In his case, we're looking at data distributions. So we're not looking at means anymore. We're not looking at variances. We're looking at distributions in this case here. And we're trying to see if distributions between a couple sets of data are significantly different than each other. Okay. And they're not all, I'll get to this in a minute, I'll say it again, but the fact that there's more than one kind of chi-square in the world, but they are all based on this same equation for calculating the chi-squared coefficient. The chi-squared coefficient, which we calculate one, we're back to the old game where we compare it to a critical value and see if which one is larger than the other, and from that we determine if there's a significant difference or not a significant difference. This is the equation. So this is the symbol for chi-squared. So basically, which is the sum of the observed measurements minus the sum, so basically it's the observed measurements minus the expected measurements. That's squared, and then it's divided by the expected measurements, and then for each of your observations you add those up, so you get a sum. Okay, chi-squared is one of those. It's a lot easier to do what actually out than it is to explain. Okay, so again, so it's used to determine, are these distributions the same? I'm looking at these data here and how they're distributed. Well, you know, I looked at that same data 5 years ago, and it was kind of distributed like this. Is there a significant difference between those two data distributions? There are two types, and I'm going to give you a case study for each one of these. Okay. The first one, okay, so they're not nesting right now, but they were nesting. So mockingbirds nesting in West Tennessee. Let's start with that idea here. Okay, so let's say you're a scientist, you observe mockingbirds nesting, and you see this, they're out in trees and all this sort of stuff. And the scientific question that pops into your mind is, do mockingbirds prefer certain tree species over others? Okay. This example here, I'm going to preface with the fact this is a highly simplified example. I'm only going to be talking about one chi-square. If you really wanted to do this, if this was your project for real, you'd be doing several chi-squares to get the data right. But so just bear with me. This is a very simple project here. So we want to find out if certain tree species are preferred over others. So the test you would use here is known as the chi-square goodness of fit test. Okay. Does this distribution of data fit this other distribution? Was what I am observing, is that what I expect to see? Is there a difference from what I expect and what I actually observe? So that's what the whole thing is about. So, okay. So the possible hypothesis you have with chi-square. Okay. The null hypothesis, of course, and this is the one we're trying to shoot out of the water. The null hypothesis is mockingbirds show no preference to tree species. They don't care what tree they're in. They're in a tree, and that's it. Okay. Another way of phrasing that, same thing. You could say it is, there's no significant association between mockingbirds and tree species. So there's just two different ways of saying the same thing. So I just didn't want to kind of constrain you to just one thing. So this is the null hypothesis. The alternative hypothesis, which of course that's the exciting one. That's the one we're trying to, basically, this is the one we're shooting out of the water. If we shoot this one out of the water, then we support the other one. So our alternative hypotheses are the mockingbirds do show a preference for tree species. Or you could possibly say there is a significant difference in the association between mockingbirds and tree species. That makes sense so far. Any problems with that? What we're trying to find out. So, because let's say you're one of those people like me in the world, you hate mockingbirds, and so if there's an association with tree species, I'll just cut down all those trees to get rid of, because I'll do anything I possibly can to get rid of mockingbirds. I hate them. They're up there with pandas. He hates pandas. Yeah. Okay, so you go out and collect data. Okay, so what you do is you go out, you're walking around, you're checking all these trees for the presence of mockingbird nests. Okay, and once you find a mockingbird, oh, there's a mockingbird nest, you call on your vast knowledge of data from dendrology, and you're going to identify that tree. Okay, and so here are your results. Okay. Turns out you found in your study 60 mockingbird nests. Okay, and these are the trees you found them in. You found 13 in redbud, 14 in Osage orange. Do we know Osage orange?
What up?
There it is. Thank you. Okay, I wanted to know if you knew the other name of Osage. And down here they're often called bodar. Okay. Yellow poplar, 11. Green ash, 10. Blue spruce, 5. River indigo. Ooh, yeah, there's 6 of those. And a violet tree. There was 1. I just found these tree names and I like them, so I used them. Okay. This is what it's called bogus data. So don't, yeah. So I found these 60. So 7 different tree species, 60 different mockingbirds. Okay, so there's my data, and I'm wondering, is there a preference? Do I see, is the distribution of mockingbirds in trees got something to do with the trees? Okay. So basically, what these are, what you're looking at here, these are called your observed data. This is the O. So you've got, so we're going to be summing up 1, 0, 2, 0, 3, 0, 4, 0, 5, eventually, not right yet. We got to do some stuff to it. Okay. Now we got to figure out what the expected would be in this case. So let me ask you this. I've got 60 mockingbird nests. If there was absolutely no preference to any species, any tree species, how would those nests most likely be distributed among these 7 species?
Evenly? Or random?
Hopefully not random, we'd be dead in the water. Okay, so basically, Lily has suggested that they might be evenly distributed. Does that make sense?
Yeah.
Does to me. Okay, that basically don't care. Okay, like I said, I've simplified this data because really what it would come down to, what if I only had 1 redbud tree? We're assuming I collected the same number of each one of these trees. Okay, in a real study, I would have had to do another chi-square even earlier. But like I said, it's highly simplified here. Okay, if mockingbirds have no tree preference, just how would you expect these 60 species to be distributed among the 7 trees? Okay, I would take the total number of mockingbirds I had, divided by the number of species of trees I have, and basically it would be approximately 9. Okay, so that's basically what it should. This is basically what I was expecting here. Right? Okay. This is your expected data. Okay. So I now have. So the only thing I need for this equation are 2 things: observed data and expected data. So this is how I would expect them to be. This is how they were lined up. Okay. So whenever you're doing a chi-square, first thing you set up this observed column and your expected column. That's where all the work is involved in a chi-square, is identifying what the observed is and identifying what the expected is. When you add up those 2 columns, they had jolly well better be the same number. If they don't end in the same number, you're in trouble. Okay? Always watch for that. If you find something different, if they don't, you needed to work with your data a little harder. You need to normalize your data. And I'll talk about that in a minute here. Okay. The remaining calculations are a piece of cake. So first calculation, observed minus expected. There's observed minus expected for each one of those. Okay. If I added those up, what would they come down to? They'd come down to 0. Not very useful. So to keep that from happening, just like what we did in standard deviation and variance, once we subtract them, we square them. Okay? So that these are our squares, observed minus expected squared. Then the last thing I do is divide each one of these numbers by their expected. Okay. That's what I get here. And then the last thing I'll have to do is add them up. And this is my calculated chi-square value. It's the sum of all these down this column here. And it's 15.6. So what does that 15.6 tell you? That's the correct answer. Absolutely nothing, right? We don't know nothing yet. What do we got to do when you calculate a value? What do you have to do?
Find the critical.
You have to find the critical. You have to get out your hymnal once again. Okay? I was lucky. So,
Nice catch.
so our critical, so this is our calculated value. Our critical value, again, is the same thing. We want an alpha value of 0.05. And unfortunately, in this book, there's only one chi-square table, and it is already at an alpha value of 0.05. Okay. What you have to calculate here first before you, so all the table is the same, but we have to know what the degrees of freedom are to calculate what row on the table. Degrees of freedom are, all you do is you add up the number of trees you have and minus 1. So 1, 2, 3, 4, 5, 6, 7. What's our degrees of freedom?
6.
6. It's highly common.
This is still pretty low. Yeah.
So, and if the calculated is greater than the critical, we're going to reject the null hypothesis. Go to page 95 in your hymnals. Okay. Usually where mine is, I think. Yes. What's the degrees of freedom? Excuse me, 6. What's the critical value? 12.6. Now what do you got? What did we just figure out?
Critical value.
Uh-huh. What did it tell us?
If it
Okay, what does that mean? What does that mean?
they're not significant.
I am not a mathematician. I'm the guy who owns these trees. So, and you want me to pay you for what? For telling me a critical value is up? Tell me what happened here.
They're significantly different.
Association between the mockingbirds and the trees.
Yeah, don't just say significantly different. Say what Courtney's saying here. What does it mean? It means it appears that there is a preference. Mockingbirds have a preference to certain trees over
It's
others.
still also this one too, right?
Okay? So that's what we found out. Okay. So let's try one on our own. Does everybody have paper they can work on? I went to get some and forgot. Okay. We're going to try a project here. Okay. Blood types. How many blood types are there in the world? Not counting pluses and minuses.
5, 4, 3, 4, 2, 1.
What blood type are you?
I don't know.
Oh, there's one.
Red.
There's one in every crowd. Okay. There's one.
A,
A,
B,
B,
O.
A, B, O. Okay, so we got A, B,
A,
A, B, O. Okay, so there's 4 blood types.
So I said 3.
Okay. Well, that's wrong.
Wait.
You're welcome.
A, B, O.
A, B.
A, B.
That's 2 different ones.
Okay.
A, B,
A, B.
and O.
So 4.
4. Right.
Okay.
Yeah.
I
There's
also
4.
said that one.
Yeah. Okay. There are 4 blood types. That in itself was exhausting, wasn't it? Okay. 4 blood types. For males, there are 4 blood types. What about for females?
Hey, I brought the book.
4. Okay. That's right. Okay. Yes.
I
Males have 12 sets of ribs. How many do females have?
13.
Where do we still believe that crap? They got 12 as well. Get your head out of Genesis. Okay. They got 12 as well. Okay. I didn't know that. Yeah. Science is weird. Okay. All right, so my question is, so there are certain females, some females are A, some females are B, some females are AB, some females are O. Same with males. Do those two distributions, are they the same or are they different?
Who knows?
Well, we're fixing to begin to commence to find out, aren't we?
Yippee.
Okay, so these are the percentages for males. A's 25.43% males. B's, okay, males, B's are 34.19% are B. Males, AB 12.5%, and O 27.86%. Okay. Females, 26.2% A, 37.0% B, AB 13.32%, and O 23.49%. These are percentages of in the United States regardless of ethnicity. So that's what they're at here.
Is this real data? Just curious.
These are real data. These are real data.
This
Okay.
one real quick.
Yeah. Didn't make this up. Now, my question is, and the wording here is important. Do females differ significantly from males? Find out. Have any questions for me? Ask them. If not, use chi-square, goodness of fit, to determine what is up with that yo. Don't know where to get started? Ask me. If you know where to get started, start. While you're doing this, I will sing show tunes. Probably not a good idea. Them the plane.
Mommy, don't you dare stop.
And we belong to his ground. I get my
I officially dad. Oh. So that's, I mean, do you want some
Oh, yeah. By the night, all day long, I really people.
Because we've been given spec and
Ever written.
before now, just check the book. Okay, so when we're finding it here, we're trying to find a. We're trying to find things to a different.
But we had to go to each one.
I'm so sorry.
So.
Right, well, that's the first trick. Which is which? None, you don't,
Oh, yeah, I
you
guess
can't
so.
randomly or willy-nilly.
It's
Pick one. One of them is observed, one of them is expected. Look at how I phrased that sentence. Now, we're getting to the crux of the biscuit here.
Is that what you're saying?
One of them's observed,
Oh,
one is
but
expected.
anyways, I specifically wanted to
And
clip.
which one is
from, like, a couple
observed and
classes
which one is
ago
expected
Where he's talking
is
about
said
how
right
he's a
in
grab
here.
Nazi and he just looks in deadpan at the rest of the class and goes, I will destroy you. Pretty much. Which one do mosquitoes like best?
Neither, that's a bunch of hooey.
Is it?
Your mosquitoes don't know your blood type.
Sure they do.
Bull monkey. No,
I think they do. Source?
And they said,
they do not know blood types. Mosquitoes have no, we could do that. We could take a number of people in the woods, we're gonna need an IRB for this, by the way. We'll take a number of people in the woods, we'll get known people,
Doubt.
we'll use the same sex people, and we'll get equal concentrations of people with A blood, B blood, AB blood, and O. Take them into the woods, see how many times the mosquitoes land, and use a chi-square goodness of fit, and I'll show you that there is no significant difference.
They do prefer different like parts of the body though, don't they?
Exposed. Yeah. Softer skin, yeah. They prefer softer skin, like that one right there. Yeah. Yes, yes. Remember, but primarily they're being drawn to carbon dioxide.
Yes, that.
And then there are certain factors such as trace organic compounds such as butyric acid, none of which are associated with your blood type. It's up there with females having more ribs.
They like
It ain't. It ain't one of them things.
they like feet.
Here's another good one. Answer this one. Which weighs more? A gallon of oil, of vegetable oil, or a gallon of water? Which weighs more?
Neither. They're both a gallon.
What?
They're both a gallon.
Gallons of volume. Not
Well,
of weight.
now I feel silly.
Of course you feel silly. You're supposed to feel silly.
If you-
A gallon of water weighs
Kilogram
more.
of fiber.
How do you know that?
Kilogram of steel.
Well, how do you know it's more dense? Oil floats on water. Excellent. How's these coming, by the way?
Terribly, because I can't focus.
Okay, so.
Slowly.
Nope, that's only in that last case. And it doesn't apply in this one. In this one, I am actually giving you the expected value. They're right up there on the board. So again, does the blood type distribution of females differ significantly from males? Which one of those is observed, which one is expected?
Mine doesn't. I have none.
2 points, take down, right there. Courtney's got it. The males would be the expected. Does this differ from that that we're holding up as males? So this is your observed, this is your expected. Now you're back to the races. None of this dividing stuff in half, there's no reason for that. That was only worked in that previous problem.
Okay, cool.
Okay, now we get to work. So I sing more show tunes.
So the males is the expected.
Males are the expected.
Would it matter either way?
Oh, heavens, yes.
Okay.
It can matter.
Okay.
You're going to get a completely different set of numbers because you're observed by, remember, you're dividing by the expected. So that's a big thing.
Right.
And if you could just use a whole different set of numbers for your divisors.
Okay. And does that relate specifically to like our hypothesis too? Because we're testing
Yes.
female distribution from
Right,
male?
yes,
Okay.
right. So we're trying to say, so basically what I'm saying is I got these males, are females the same?
Okay.
I would expect these males and females. Okay, so now we should be getting some answers.
Maybe.
Are you doing it as an Excel file? Excellent. No, I was lauding you.
Okay.
That's right. That was a positive thing.
No, that's the wrong game.
No, I agree. They always look like they're on speed or fat. Yeah, yeah. That's just to show skull speed. Mhm. Just simple stuff. Did you? I did theirs last time. Really? Yeah. Yeah. It was. Yeah, I'd be happy to. Really? I did. I did that school. 5 years, 6 years ago. Really? Yeah, I did that school. Yeah. It was a dead of winter, and basically I didn't have a clothes. Busby had what he got from Goodwill. Coat. You want a coat?
I got a guy.
Yeah, remind me to send you over. Oh, yeah. Of course you will. Yeah, but no, I did that one. Got to see my speed.
Let's see, what?
I see, yeah. Not real close.
But I think you're right, so it's following the equation, so you
Right.
should
Right.
we don't do that, we don't do that.
So, it just,
So small,
already gone. Oh, that's after.
You did, yeah, you
Yeah, I
divide
did.
before you do the sum of it all.
Okay.
Maybe Native American. Latina and Native American primarily.
That divided by.
Yeah.
So they many different things.
It's divided by the expected.
Scrubland.
Probably wrong.
Yes.
That's up against the front range, south.
Yeah, so it's basically short grass prairie. Yeah, I'll be darned. Which, so it's your natural resource. Wildlife. Yeah. Yeah. Maybe that's why I did such a great job. Maybe we get someone else to do it.
I think I got it wrong, but I did it.
Good job. I'm very proud of you.
You kind of got me confused.
Squares, dude.
Yeah, we're talking about square.
But we're already doing this.
I think you should do it.
What am I doing?
Okay, do we have any answers yet?
No.
Do we have a calculated chi-square value?
No.
Who has a calculated chi-square value? Raise their foot. Okay, what is your calculated chi-square?
1.007.
1.00, so what did you get?
I just rounded to 1.
That's fine, yeah. On chi-square, remember my rounding rules don't really apply on these because if you've got those values down there, so everybody's fine. That's your calculated value. What's your critical value?
7.81.
We got to find it.
Okay, let's see what I have to open the book up here. Let it close. Okay, so what's your degrees of freedom?
3.
3, 7.81. What have we learned from this little exercise?
There's no significant difference between the blood types.
We find no significant difference between the blood types. Basically, how you would say it. Doesn't mean there isn't one, maybe, but I seriously doubt there is. No, there's no difference. We don't see a difference. Okay, everybody's good with that?
Wait,
Okay.
so is it? The difference in.
Probably have some more of these.
these.
We'll wait on that. We'll take it on the
No.
next one.
Wrong page.
Okay, so here it is. So again, pay attention to the wording. What is
you
the
were on
null
the wrong page
hypothesis?
earlier,
What is
but
the
you
alternative hypothesis?
No, I wasn't.
The null hypothesis is there's no significant difference between the two of them. The alternative hypothesis, there is a significant difference in distributions. The observed values you decided were the males, and the expected, or the females rather, and the expected values are the males. Degrees of freedom you had 3. Okay, done with that. Let's go to a different problem that deals with distributions. This one is just as easy, but not, okay? It's the same equation, only there's a little bit more mental work in here. You have to play around a little bit. Okay, so here's this next case study. This is a soldier beetle, family Cantharidae. Okay, I like soldier beetles because I often find them on Solidago, better known as goldenrod. Okay, so everybody, if you've lived in this part of the world any length of time, you have seen this very thing here somewhere. Okay, but sometimes I see these guys on other plants just as well. Okay, so that begs my scientific. So my observations are: I see soldier beetles on flowers. Seems like I mostly see them on goldenrod, but I do see them on other flowers. So, are soldier beetles primarily associated with goldenrod? Is there something going on between the two of them? Becomes my question. And the test to do this is also a chi-square. Only this is called the chi-square test for independence. Is the distribution of soldier beetles independent from the distribution of goldenrod, or is there a dependence between one and the other? Becomes the question. So how would we do this? Okay, again, two possible hypotheses. The null hypothesis in this case is there is no significant association between soldier beetles and goldenrod. Okay, so if you find them on goldenrod, they're just as equal as you could find them on any other flower. Okay, here's another way of saying that. Soldier beetles and goldenrod are independent of each other. Again, just two different ways of saying the null hypothesis. I don't want to lock you into one. The alternative hypothesis then, okay, oh, no, I got yet another one. Sorry about it, I forgot I added the third one. Okay, so you can also say then, the location of the goldenrod, where I find goldenrod, doesn't have an effect on where I find soldier beetles. So these are three all the same thing. Okay. My alternative hypothesis would be this then. There is a significant association between soldier beetles and goldenrod. Soldier beetles and goldenrod are dependent on each other. We see them, there's some sort of relationship between them. And then finally, the location of goldenrod has an effect on the location of soldier beetles. Making this sort of conclusion because it's hard to imagine the plants getting up and moving to the soldier beetles. It's probably the soldier beetles moving to the plants. Okay, so we're going to collect data. For this study, to collect data for this, what we have to do is we're going to set up plots. Okay, just randomly set up plots in the area in which we're interested in. Okay, so these are randomly selected plots, and then we're going to go to each one of these selected plots designed, and some of those plots are going to have goldenrod in them. Some of them are not going to have goldenrod in them. Some of them, okay, then when we get to these plots with and without goldenrod, we have a bunch of both, we're going to look for soldier beetles. Okay? And so as a result, each one of our plots will be of one of four types. Okay? One type will be, I found a plot, it has goldenrod in it, and by golly gosh, there's soldier beetles too. Okay, you can see where I'm going with this. The next one would be, it's got goldenrod, but I don't have any soldier beetles. Third type will be, I ain't got goldenrod, but I do have soldier beetles. And the fourth type, I got neither. Okay, there's no goldenrod in this plot, there's no soldier beetles in this plot. So this is how we're going to set up our data, and now we're going to go out and sample these plots. I can't remember how many I've stuck into this. Okay, I'm going to collect my data. Okay, and then I'm going to put this into what is called a chi-square contingency table. Okay. So we've messed with contingency tables before. We did that when we did post hoc tests. Okay, so here's how I'm going to line this up. So my table, I could have goldenrod and with soldier beetles. I could have goldenrod alone. I could have soldier beetles alone. I could have neither. Okay? So with goldenrod and soldier beetles, goldenrod, no soldier beetles. Soldier beetles, no goldenrod, no goldenrod, no soldier beetles. That's my contingency table. So it's just so far I haven't done anything. I've just collected my data, and now I'm going to put them into the Excel file or on your table and in paper this way. And what you do is you're going to have a certain number of plots here and a certain number of plots here, and you're going to sum them and put it there. Okay? So that's my top row sum. I'm going to do that again. That was so much fun. I'm going to take plots with just soldier beetles, no goldenrod, with neither, and sum those up. And that's my bottom row sum. Okay, now what? We did it for the rows, let's do it for the columns. Okay? So I get these two, sum it up. I get these two and sum that up. Okay, with me so far. Now, what should I stick into here? The sum of which one?
Both.
The sum of all four of the column and row sums.
You're only going to do, you can either do the sum of the rows, or the columns, or the sum of the columns, or the sum of the rows. You can put it here. Which one would you do? Doesn't matter, does it? They should be the same number. Because it's the associative law of mathematics, that if I sum these up and sum these up, that sum is gonna be the same as if I sum those up, so it's the same number. Okay, it's either the total row or the total column, it's the same thing. So that's my contingency table. So what you did here, this is your observed, this is what you collected in the field, these 4 data points. You then summed. Okay, this is your observed data. Okay, so that's what we observed. Now we've got to calculate expected data from this. Okay. And this is a little bit, this is kind of mathematical. Okay, to calculate your expected data, what you do is you take your sums. Okay, so you take the top, so the calculated data here would be I take this, multiply it by this, divide it by this. If I want this one, I take this one, multiply by that one, divide it by this. If I want this one, I take that one, divide it by this. Follow what I'm doing. So any one of these squares, the expected is going to be what the column sum was, multiplied by what the row sum was for that column, and divided by this. That's the weirdest part, get your head around that. Okay, so left column sum plus top row sum, multiplied by top row sum, divided by total. Left column sum, bottom row sum, divided by total. Right column sum, top row sum, divided by total. And right column sum, multiplied by sum, bottom row, and divide, okay? You now have your expected data. So you have the first little table you did was your observed. Now you've got your expected. And now you can do this equation. I'm going to show you an example of all this in a minute here. Okay. So you end up in your mind, what you should be when you're working this problem, you're going to have 3 separate tables. And the upper table is your observed data. Okay. From the observed data, you calculate your expected data in the next table. Now you're going to use both of those tables together to calculate observed minus the expected for each data type. Okay. Once you have that, you're going to sum those up either way again, and it gives you your chi-square value to compare to your critical. Okay. And it's the same thing as before. So let's look at this now. Let's try some data. Okay. You sample 150 quadrats. Okay. Those with both goldenrod and beetles present, 76. Goldenrod present, but no soldier beetles, 16. I think I'll start writing these up on the board to get you started. So the first thing here I got 76. Okay. Goldenrod present, but no soldier beetles, 16. Goldenrod absent, but soldier beetles present, 18. And finally, neither one, I got 40. Okay. So I've started my table. I'll leave it right here. What's the first thing you do?
Start adding across the rows.
Adding across the rows would be a good idea. So. I could have done that differently, couldn't I? Okay. 76 plus 16.
92.
2. 80 plus 40.
58.
76 plus 18.
94.
94. 40 plus 16.
56.
The total.
150.
You got 160, what was it?
150.
150.
Yeah, better be. Yeah. So these are my observed values. Okay? Now we gotta calculate the expected. I think I needed this. Go ahead. Okay. So what would this observed value, what would this expected value be? Anybody? How would you calculate?
94 over 90, or 94 times 92 divided by 150.
90, so what he did was, I'm trying to find this slot here, which is equal to this one, I'm gonna take 92, multiply by 24, divide by 150. What do you get when you do that?
57.7.
Give me full. 58? Okay, 58. Running out of ink. Okay. Next to it would be this square. What do I gotta do? Who are my players?
92.56 divided by 150.
What is 92 multiplied by 56 divided by 150?
34.
34? That seems right in my head. I've add these up in my head. Now what?
$36 on the middle left.
This one is, so this one is 14 times 58 divided by 150, and you got 36?
Yep.
Okay, and then the last one,
22.
42.
22.
22.
I knew that, 22. I'm gonna erase these because we don't need them for anything. I got the result too. Okay.
Still can't hear.
So these guys here, these are expected, observed. These guys are expected. And now I want you to calculate the observed minus the expected squared divided by the expected. How are you gonna do that?
The same way we done did it.
Okay. You're gonna take the observed, 76, minus 58, square it, divide it by 58.
Five and a half.
5.5.
Yes.
Sure, we'll make 5.5. Why not? Okay, now I want this value, which is going to be observed 18 minus 36 squared divided by 36.
9.
9? This value is 16 minus 34 squared divided by 34.
9.5.
9.5. And last but not least, 56 minus 22.
40 minus 22.
40. Oh yeah, I moved that. Okay, still 40. 40 minus 22 squared divided by 22.
14.7.
Okay, 14.7. What is the sum of those? And that's going to be our chi-square calculator.
38.8.
38.8. 8.8. What is the critical value?
7.81.
What were your degrees of freedom you used?
3?
That is correct. 3 degrees of freedom, 7.81 is the critical. Okay. Besides it giving you a headache just now, what else do you know? Well, what else does this tell you?
That the differences between where golden rod and soldier beetles are both present are significantly different.
What does that mean? What did you just say?
I'm
I
trying
don't
to
remember
think.
that's what we were testing. Again, remember, I'm always going to rip you back, spraining both of your ankles. Why did I do this? What am I showing here?
Well, actually, we don't really know.
Right?
That the
Something is significantly different.
Something is significant. What is significant?
I don't think we know.
Chi-square test for independence.
goldenrod and the soldier beetles are dependent of each other?
There is an association. It appears there is an association between the distribution of goldenrods and the distribution of soldier beetles. It is significant, a significant association between them. So, yeah, looks like the goldenrod. I know it's that way because this when I made up this data, that's what I put on it. It's bogus data. Okay. So those are the two different tests. Okay. So let's try another test. Let me see if I can find one. My vast array of notes. With chi-square, really what chi-square comes down to is a lot of time on task just to learn. It's not that tough. Let's see if I have a test here somewhere. Lectures, that's not what I want. Oh look, chi-square problem. Let's try that one. Okay, we'll say that one for next. That's a good one too. Okay, this one here, because this is a good one. Okay, so trapping. Everybody likes to go trapping. I use that one because I got these pictures. So using tomahawk traps, okay. I was trapped on a WMA here in West Tennessee in 2021. Okay, I set out. This is basically what I got in my collection. I got 2 armadillos. I got 34 opossums, a feral cat, a 4-striped skunk, and I also got, this is a good one. Yeah, this is a good one for you to do. And then I got 78 raccoon. Okay? Great. Big deal. That was in 2021. This year I went back and hit the very same ones. I happened to get the same 5 species, but this time I got 4 armadillos, 18 Virginia possums, 13 feral cats, 2 striped skunks, 41 raccoons. This is more likely what you're really going to see when you do chi-square data. And there's some important steps in here. Okay. So I'm going to ask you, does the species composition that I observed in 2021, okay, or first, does it differ? I got that backwards. That's not going to make any sense to anybody, not even me. How can I split that? Okay, so that should be, come on. There we go, 2023. What's in there? Okay. Actually, okay. There, now. Yeah, okay. I'm losing ground.
I've never seen something progress and also come backwards so many times.
I don't like this keyboard. I'm gonna go over here, go like this, and just simply erase all this. We don't need any of that. Yes. No. So close. Okay. Screw it. Okay. The question I'm asking is, okay, Does the data I observed here differ significantly from what I saw in 2021? Okay? So I want you to calculate that out. So let's get us another table here. So let's maybe erase all this, and we'll work on this in a minute, because this is what a real chi-square. What I've given you so far has been nice and sanitized data. These are real world data here. They're still voters, but they're still real world data. So we need a better marker. So I've got 5 species, right? Okay, so here's my species. 1, 2, 3, 4, 5. Okay. What is my observed data?
The ones in 2023.
Everybody agree with the ones in 2023?
Yes.
Okay. So my observed, so what are those values?
4,
18.
4, 18,
2, 41.
18, 3,
2.
2,
Oh, sorry. My apologies.
41. And what do those add up to?
68.
Yeah, who?
68.
68, thank you. 68. Okay. Next question. That's the observed data. What's the expected data?
The 2021 data. No. Yes.
Let me show you something.
Okay.
Okay. So you're thinking right offhand, well, cha, the expected data is going to be 2021. No. What are the 2021 data?
2,
2,
34.
34,
1,
1,
4,
4,
78.
78. Add them up.
119.
119.
119. Okay. What did I tell you? He said with arms akimbo.
It must be the same.
Those 2 columns must be equal.
Ah.
And it's not. It's not equal. What are you going to do about that?
Cry.
No, you're not going to cry. You're going to say, I know how to fix this. Okay. This is the distribution we expect if we caught 119. What you want, what would this distribution be if we caught 68? How do you do that? How would you figure that out?
Calculate the percentages and then multiply by 68.
You don't even need a percentage, you use a frequency. But you know what the difference between frequency and percentages?
Frequency is a whole number.
Well, not a whole number. Percentage you multiply is a frequency multiplied by 100. We don't want to multiply by 100, we just want the frequency. Okay? How do you calculate a frequency? Number by the total. Now we are off to the races. So this is all well and good and fine and dandy, but it ain't what we want. So my expected value would be, for this one, would be what? If you did the math. Don't give me the equation, just do the math. It would be what? 2 divided by 119 multiplied by 68. There it is. Now you're about to solve all the world's problems. There will be peace in the Middle East when you're done. This is great. Okay? So, now, this will be 34 divided by 119 times 68. So, now you're going to be giving me all those numbers. I'll let you go a while, then I'll ask who has the numbers. This is the interpretive dance.
If you say so.
You know you're gonna need an econ degree, did you? Okay. Anybody got any of these numbers yet? What's our first expected?
1.1.
1.1. Yeah, okay, that's all right. Next expected,
19.4.
19.4. Followed by
0.6.
0.6. Followed by
2.3.
2.3. Guess that. Then 78.
44.6.
44.6. Do you think you're right? How would you check these numbers?
Add them all up.
Add them all up and what happens?
They should equal 68.
Do they?
Yes.
Lie to me. Doesn't matter. 68. Okay. Now you're off to the races. Now you have the players. Now you can calculate chi-square. So here's your observed, what we expected. So you can do this. After you do this, you can do this. And since that was so much fun, you're going to do this. And then you're going to sum them up. You get the chi-square calculated. Go E4. I think it's not a real skull. No. Sometimes they use a real skull and you can buy these Cummings or, yeah. Well, I don't like the bipedal thing, so it's got that Puss in Boots thing going on. Whoever ruined this, put in Reganza, it's really, that's, yeah, they messed up the beacon. Frank Belrose, Butterfly, turning in his grave right now. Where are we at?
Done, I think.
Done and done? Anybody else done and done? What was your calculated chi-square value?
38.3.
Would you agree with that? No, you would not.
No, did I do
I
it
got
wrong?
17.63.
I was gonna say, I got 17.6.
No, I did it wrong.
17.63. I'm going to go with that if that's okay with you.
Sure, I'll allow it.
17.63. What would be the critical value? What's our degrees of freedom here? 4. 4 degrees of freedom. So our critical value is?
9.49.
Well, so what's happening on this West Tennessee WMA? Time to come back to reality. What's it telling us? What?
That the species composition in 2023 differs significantly
There's been a change. Something's going on.
from the.
We're finding that the distribution of mesomammals has changed significantly over this period. Chi-square doesn't tell us exactly how it's changed or anything, but it now drives our research. one more trap problem. Oh, jeez. Okay. So when I was out trapping these traps in this trap here, I noticed something else. Okay. What baits do we use to trap in a tomahawk trap? What's the standard bait? Cat food. What's the other bait?
Fish.
What kind of fish? Sardines. Okay. So I trapped some traps with sardines and some without because I wondered if there's an association, because let's face it, opossums like sticky things. So I was wondering if there's an association with the things that I get with sardines and without sardines. Okay, so I looked at how many traps I had with opossums. I gotta do it this way. So, okay. No, that's all right. Okay, with opossums, without opossums. I'm not using writing with traps where I got with they didn't have an opossum in them. Versus traps that I use sardines or not sardines. Here are my data. Awesome, with, without 15. 63. 12. 110. Okay. My question is, based on this, using chi-squared test of independence, is there association between opossums and sardine bait? I'm going to sneeze. So what's the first thing you'll be figuring out? What is that? What will it be? What will this table be? Starts with an O. Observe.
It was just sums, right? Not means or anything.
Mm-hmm.
So this is the easier part. So I'll go ahead to the right, everybody okay with this on our observe? Okay. Anybody have any of these expected values yet? Okay.
Maybe
So, Caitlin, give me the first one.
10.53.
Okay, I'm gonna go with 11. Next one,
16.47.
I'll go 16. This one,
67.47.
67.
And 105.5.
106. Okay. Okay, so there we're going. These ones you can do to 3 decimal places, without any problem. Have we got these values yet here? Anybody want to give me one? So what would be this value right here?
1.5.
1 who?
1.5.
Oh, it's got higher than that. 1.898.
That's what I got.
Yeah. 1.898. Okay. Next one. To the right.
I got one.
The next one.
3.51.
Okay, I'm doing
I got one as well.
Is that the final value?
No.
No.
Why am I struggling?
I got for this one 1.213. Anybody else got that?
I mean, I got straight up 1.
I got one as well.
You got one?
Yeah.
Okay, I'll go with your one.
How do you get 15 minus 11 squared
Okay.
divided
What'd you get for this one?
by, yes.
0.239.
Wait, what?
0.239.
I got-
I was close to that. I was 0.296. 239. That's not gonna make a difference. I'm gonna make your number there. And the last one?
0.151.
Yeah, I was 189. Okay, good enough. That's still gonna be close enough. What do those add up to? All together they spell mother.
Oh boy.
So, go ahead and add up yours, whatever you got. It's gonna be close enough.
2.94.
2.94 hours to 3.5, not a problem. Okay, so what does that tell us? Or did we forget again?
Oh. It tells us the. Wait, hold on.
So you're shaking your head. So, again, I'm the landowner and I asked you something, you just shook your head.
It doesn't tell us anything. It tells us nothing yet.
Okay, so
No, it does tell us.
say it a little bit more. Yeah, you said, tell us nothing. What do you mean by that?
That's our calculated.
Right.
So we have to compare it to our.
Okay, I already did it. So compare it.
Oh.
Here, you use 3. Yeah, same thing.
Yeah.
Okay.
So that is, so our calculated chi-squared is smaller than our critical chi-squared, so there is,
No significant
No
association between sardines and
So
possums.
it appears we don't see a preference of opossums with sardines. And that's it, that's Times Square.